So this is the fifth session on friction. In this video also I'll take up two more numerical problems on kinetic friction. Okay. I'll take up two more numerical problems on kinetic friction. Okay. So if I'll take the file, first write down the first question of this video. Question is this. A small block of mass m rests on a rough inclined plane which makes an angle of theta with the the friction coefficient between the is mu is equal to 4 tan theta. Okay. What minimum horizontal force F should be applied to the block as shown so as to just cause it to slip up the inclined plane, so as to just cause it to slip up the inclined plane. Answer should be in terms of mg, where small g denotes acceleration due to gravity on the surface of Earth. Okay, fine. I'll rub this, okay? First, I draw the diagram of the situation. This is the horizontal. This is the rough fixed inclined plane. This makes an angle of theta with the horizontal. A small block of mass m lies here. Friction coefficient between block and the inclined plane is mu, which is given to be 4 tan theta. Rightward horizontal force F is applied to this block as shown in this. This force is horizontal, so this theta, this also is theta. Corresponding angles, okay. Now we have to find the minimum value of F so that the block begins to slip up the inclined plane. Okay. First what I do, I draw the free body of the block with respect to ground. Mg, F. N is the normal force on block due to the rough inclined plane. It is required in the question that the block should slip up the inclined plane. So inclined plane should exert a friction small f on the block down the inclined plane, opposite to the direction of relative slip. Okay. Now what I do, I assume that force is just sufficient to cause the block to slip up the inclined plane. Okay. So let A be the corresponding acceleration of block up the inclined plane when the force F is applied to it. Now, since the block begins to slip, since the block begins to slip, the inclined plane implies A is more than 0. This means MA is also more than 0. M is the mass of the block. A is the acceleration of block with respect to ground. Now from this free body, I apply Newton's second law to block up the inclined plane. So F cos theta minus mg sin theta, component of weight down the inclined plane, minus F is MA more than 0 from Newton's second law. MA is equal to this much. So this means F cos theta minus mg sin theta minus F is more than 0. Now the block is slipping over the inclined plane. So therefore F should just be equal to mu times n. Okay. Now how to determine the value of n? To determine the value of n, I apply Newton's second law to block along n. In this direction, this F has no component in this direction. So if I apply Newton's second law to block with respect to ground in direction of n, what do I write? N minus mg cos theta minus F sin theta. That is equals to mass times acceleration of block with respect to ground in this direction, which is simply ma cos 90 degree. But cos 90 degree, you know it is 0. So this term goes away. So right side becomes 0. So n becomes mg cos theta plus f sin theta. Now this n I substitute in this, I get f is equal to mu times n plus f sin theta. Okay. On this, if I substitute in this inequality, alright. Now I rub this one. So I substitute this f in this equation. F cos theta minus mg sin theta minus mu times mg cos theta plus f sin theta is more than 0. Okay. Now mu is given to be 4 tan theta, that is 4 sin theta by cos theta. So substitute the value of mu in this inequality. Mg sin theta minus 4 tan theta into mg cos theta minus 4 tan theta into f sin theta, that is more than 0. Okay. Now I take f common here. Cos theta minus 4 tan theta becomes sin theta by cos theta into sin theta. Okay. This is more than mg and these two terms I shift to that side. Plus 4 tan theta becomes sin theta by cos theta. Mg cos theta. Now cos theta goes away. So right side becomes 5 mg sin theta. I rub this one, okay. Now shift cos theta that side. I write it as f into cos square theta minus 4 sin square theta by cos theta is equal to 5 mg sin theta. 5 mg into sin theta. Sorry. This is done. Okay, fine. Alright. So f should exceed 5 ng into sine theta into cos theta, cos square theta minus 4 sine square theta. This is therefore the required minimum value of force F. This is therefore the required minimum value of force F, so that the block begins to slip up the rough inclined plane. F should exceed this much value. Okay. This question also I have fully discussed. Alright. You carefully go through it. If you have any doubt, you put it in the comment box. I'll explain it properly. Okay. So first question has been discussed. Now I take another question. Rub this one. Okay. Now I take another question. Example 2. Example 2 is something like this. There is a fixed rough inclined plane which makes an angle of 30 degree with the horizontal. Which makes an angle of 30 degree with the horizontal. Okay. A small block is projected up the inclined plane with some non-zero initial speed. With some non-zero initial speed. Value of speed is not given. Okay. After moving some distance, the block momentarily comes to rest and then returns to the point of projection. And then returns to the point of projection. Also time of descent is 3 times the time of ascent. The question is, find the friction coefficient between the block and the inclined plane. Find the friction coefficient between the block and the inclined plane. This is the question. Okay. I hope the question is clear. Okay. I love this. Okay. First, what I do to solve the question, I draw the diagram of the situation. So see, this is a horizontal surface. This is a fixed rough inclined plane which makes an angle of 30 degrees with the horizontal. O is a projection point. From here a small block of mass m is projected up the inclined plane. Projected meaning it is thrown up the inclined plane with some initial non-zero speed u, which is not given in the question, which I have just assumed. As it moves up due to the weight and friction, it slows down. It momentarily comes to rest at some instant here. At this point its v is 0, and then it returns back to the point of projection. The time taken for the block to grow from this point to this point is the time of ascent, and time taken by the block to come from this point to this point is the time of descent. It is specified in the question that Td, that is time of descent, is equal to 3 times the time of ascent. Okay, time of descent Td is equal to 3 times the time of ascent Ta. Alright, fine. So Td is equal to 3 times Ta. Now you have to determine the friction coefficient between the block and the incline. Okay. Now what is one thing which is common in both the phase of motion of the block? Distance moved. The block is thrown from the bottom of the inclined plane with some non-zero initial speed u. It comes to rest after moving some distance, say L. It momentarily comes to rest after covering some distance L up the inclined plane. And here it comes to rest, and then it begins to move down and its speed begins to increase. When it comes here again to the point of projection, in the second phase of journey, that is in the downward journey, again the block has covered the same distance L. Again the block has covered the same distance what? L. Okay. Now question is how to solve the question, how to solve this numerical problem. We'll find the expression for Td and Ts separately and then substitute in this equation to get the required value of friction coefficient. Okay. So let mu be the coefficient of friction between block and the incline. Okay. So see, when the block moves from bottom to up the incline, that is in upward journey, at some instant I draw its free body diagram. Okay, during its upward journey while it is moving up the incline. See what are the forces? Mg, normal force which is normal to inclined phase. With respect to rough incline, the block is slipping up. So friction acts on the block down the inclined plane, opposite to direction of relative slip. And since slipping takes place, so F is just equal to mu n. Also, acceleration of block during its upward journey is down the incline. Now apply Newton's second law to block in along the direction of n during its upward journey. Then what do I write? N minus mg cos theta is equals to mass times acceleration a1 of block during its upward journey. During its upward journey, acceleration of block is a1 down the incline. So a1 here, a1 cos 90 degree, because a1 is down the incline and we want the acceleration of block in this direction, which is simply a1 cos 90 degree, which is 0, because cos 90 degree becomes 0. So n becomes how much? mg cos theta it becomes. This and a substitute here, I get the value of friction. Mu mg cos theta, this is the value of friction force between the block and the inclined plane. Now, as I've stated just now, while moving up the incline, block is accelerating downward with acceleration a1. Now a1 you see, F is equal to mu mg cos theta. Now what I do, see, I first determine the acceleration of block with respect to ground during its upward journey. Now as I've stated just now, during its upward journey, acceleration of block is down the incline. It has a magnitude of say a1. So apply Newton's second law to block with respect to ground down the incline during its upward journey. Net force down the incline becomes mg sin 30 plus mg sine 30 plus f, which is simply mu times mg cos theta. Here theta is simply 30 degree. Theta which I am writing here, that is 30 degree, okay. So apply Newton's second law to block with respect to ground down the incline during its upward journey. Net force down the incline becomes F plus mg sine theta. Theta is 30 degree, okay. I'll put it at the end. That is just equal to m times a1. Now F is equal to mu mg cos theta. I substitute this F here. Mu mg cos theta plus mu mg sin theta is equal to ma1, okay. So m goes away. So a1 becomes g sin theta plus mu cos theta. See, during its upward journey, acceleration of block has a constant magnitude a1 down the incline. So this quantity is constant. So during its upward journey, acceleration of block is a constant magnitude a1 down the incline. Now the block takes ta time to move from here to here. It moves with a constant acceleration a1 down the incline and covers the distance L during its upward journey. Since acceleration is constant, therefore we can write displacement L is equal to initial speed u plus final speed here 0 by 2 into what? Ta. Ta means time of ascent. This formula follows from that formula, d equal to u plus v by 2 into t. For the case of motion of body along a straight line with constant acceleration. Now how to find u? U is not given. During its upward journey, acceleration of block has a constant magnitude a1 down the incline and u is initially up the incline. Here v is 0. So apply the formula v equal to u plus at to the block during its upward journey. Final v at that point becomes 0. In upward direction I have taken to be positive. U is up the incline minus a1 ta, because v by u plus at formula, all v, u, t, they all have v, u and a have to be taken with sign. I take up the inclined plane to be positive. So u becomes a1 ta. Now substitute this u in this equation. It becomes a1 ta into ta by 2. a1 ta square by 2. Okay. Where a1 denotes this quantity. a1 is equal to g sin theta plus mu g cos theta. Here I missed out the g here. By careless mistake I put that g, okay. One g was missing, I put that g here, okay. So a1 is equal to g sin theta plus mu g cos theta. That is a1, okay. So L is equal to a1 ta square. Let's call this as first equation. Where a1 is equal to g sin theta plus mu g cos theta. Okay, fine. Now I rub this, okay. Let us consider the downward journey of the block, second phase of journey of block, that it is downward journey down the incline, okay. So again, see, while the block is returning downward, at some instant it is here, say, moving at some speed v, okay. Now what I do first, during its downward journey, I find the acceleration of block with respect to ground, okay. For that what I do, I draw the free body of block with respect to ground during its downward journey, that is during its journey down the incline. So what forces are going to act? mg, n. With respect to rough incline, the block is slipping downward. So inclined plane will exert a friction F on the block up the incline. Now during its downward journey, the speed of block is increasing and it is moving downward. So acceleration also should be in the same direction, A2 say. Okay. Now apply Newton's second law to block down the incline during its downward journey. So net force down the incline becomes mg sin theta minus F. Minus F is equal to m times A2. Now again here slipping is taking place. So F should be written to be mu times n. Okay. Now to find F we need to know n. To know n, what do? I apply Newton's second law to block in this direction, along the direction of n. So what do I write? N minus mg cos theta is equal to n times component of a2 in this direction, which is simply a2 cos 90 degree, which is 0, because cos 90 degree is known to be 0. So n becomes mg cos theta. This n I substitute here. So this means f becomes mu times mg into cos theta. This is f. This f I substitute here, we get a2. n a2 is equal to mg sin theta minus mu mg cos theta. Now m goes away. Alright. Rub this one. Now, how much do we get? A2 minus mu g cos theta. Now see, all the quantities given in the question are constant. So A2 is therefore also a constant amount. Now during its downward journey, the block again covers a distance of L with a constant acceleration A2 and starting from rest. So again apply that formula ut plus half et square to the block during its downward journey. So during its downward journey, block again covers a distance of L with a constant downward acceleration A2 and starting from zero initial acceleration, zero initial speed v, u. So second phase of journey, okay. So L is equal to 0 into Td. Td is the time of descent, plus half A2 into Td square. Alright. So L becomes half A2 into Td square. Well, A2 is this quantity, okay. L is also this one. This is the second equation. So from first and second equation we see that they are both L. So these two should also be equal. Alright. I rub this one. So these two L's are equate. So half A1 Ts square equal to half A2 Td square, okay. Now A1 is how much? G sin theta plus mu g cos theta into Ts square. What is A2? G sin theta minus mu g cos theta. Cos theta into what? Td square. Now g is a common term, it goes away, you can see. Also Td is given to be 3Ta. Td is given to be 3 times Ta. So Td square is 9 times Ta square. So this Td square replaced by 9Ta square here. G goes away. Sin theta plus mu cos theta into Ta square. Sin theta minus mu cos theta into 9Ta square. Ta square goes away. Okay. Now rub the first column. So now I simplify this. From left side we get sin theta plus mu cos theta is 9 times minus 9 mu cos theta. So this I simplify, it becomes 10 mu cos theta is equal to 8 sin theta. So mu becomes 8 by 10 sin theta by cos theta. 8 by 10 is 4 by 5. Sin theta by cos theta from trigonometry is tan theta, which I write as 4 by 5. Tan theta is 30 degree. So this becomes tan of 30 degree, which is 1 by root 3. 4 by 5 root 3 is therefore the required answer. Okay. So friction coefficient mu between the block and the inclined plane has a magnitude of 4 by 5 root 3, which is therefore the required answer. Okay. So the answer I've written it 2 times just for clarity. Okay. So this 2 problems on kinetic friction has been discussed. You go through it carefully. In case you have any doubt, you just go through it. You put your doubt in the comment box. I'll explain it there. Okay. So next video also I'll take up some more problems on kinetic friction. Okay. So this I close it here. Fine. All right.